Hello. So in this video, we'll be looking at using calculus to find a max or a min to optimize. We've got a kind of a classic problem here. We need to enclose a rectangular field with a fence. We have a certain amount of fencing material, and building is on one side of the field, so we won't need any fencing on that side. Determine the dimensions of the field that will enclose the largest area. So I am super visual, so I always like to start off with a picture. So we've got some building, and we're going to build a fence around that building. And if this is our area, we want that to be maximized. So what you'll find in a lot of these problems is that the main part of the problem is to figure out a function. And then once we've got a function, using calculus to find the max or the min, or even just graphing to find the max or the min, is relatively easy. Okay, so we know that this has some total, right? So we've got fence on the sides, and we've got fence coming on this other side. And so one thing we know is that if we add up all that fence, it'll be 500. And sometimes you'll do a problem and it'll be like up to 500. But if we're trying to maximize area, definitely we want to use all of the fence, right? Because whatever solution we found for less fence, we could just add on more fence and we'd have more area. So the area is going to be length times the width, the area of a rectangle. But right now it's not a function we can use. Right? We've got two different variables. As we change one, we change the other one. So the question is really how can we kind of make this a function of one variable, which are the kind that we're doing in calculus right now. Later on, if you continue on to calculus 3, you'll learn how to deal with functions of more than one variable. Okay, so we have to figure out s in terms of t or t in terms of s. We've got 2s plus t equals 500. So looks like it's easiest to solve for t there. There's a number of people who describe mathematicians as professionally lazy. Okay, so we've got this function. Simplify it, don't simplify it, it's up to you. I want to see what the graph of that function looks like and if it's reasonable to think that it has a maximum. So the function on Desmos, we might be able to put it in with the s, we could probably put it in with the t, but we might as well be traditional and go ahead and put it in terms of x. So x is going to be how long this side is. So for example, if we made s equal to 100 feet, and this side would be 100 feet, so the top side would be 500 minus the 200, this would be that. And the numbers that we're looking at then, the area for this one, when the side length was 100, would be 300 times 100. So we're talking about big areas in terms of square feet. That's 30,000 square feet. So one thing I'm going to notice when I come over back to my graph, it looks like I can't see anything, right? But that's just because the function we're dealing with is so big that it's not showing up on this graph. So we could zoom out. It's going to take a long time, right? So the y-axis here, we don't care about. The y-axis is f was giving us the area. So we don't care about negative areas. So we could put 0 in there. And in this one, we want something huge. We want like 30,000. That was just an example we picked. So I'm going to go crazy. 100,000. Okay. And we're dealing up to 500 feet of fence. So, well, the biggest X would be if we used half the fence, even though that doesn't make any sense, right? If it was 250 feet, that'd make the top 0, which wouldn't have any area. Okay, so here's our function. We click on it. It'll tell us what the peak is. All right, as may have been mentioned before, with the improvement in graphing technology, some of the old uses of calculus have been kind of outmoded, right? Like right now we know if we set x to be 125, that's going to give us our maximum area. And that maximum area is going to be 31,250 square feet. Okay, so what we're using these examples for is not so much just solving the problem, but thinking about how does calculus relate. Okay, so coming back over here, what we want to do is to see what calculus can tell us about this problem. So if S is 125 feet, then T is 500 minus 2 times S, which is 250 feet. Well, that's kind of interesting. So the ideal fence in this situation is like 2 squares. So it turns out nature likes squares and circles in terms of optimizing things. So it's not totally a surprise, having solved some of these before, that the square is involved. All right, so let's go back to the Desmos. So the derivative, how does it help here? Well, the derivative is where we find the optimum. So it's not showing up here. Where is it? We can see it's almost 0 on here, right? So we're going to want to change the scale to see the derivative. If we click on the line, it's suggesting a point. Oh, so it is telling us where it crosses. All right, so that makes sense. So it's positive on this side until this peak where it's 0, and then it starts going down. So by looking at the rate of change, that place where it's 0, it's done going up, starting to go down. So this has to be the place where the derivative is 0 and the function has its peak. So we don't know what that's necessarily going to look like, right? It looks small. So if we change to 200, it's not enough to see anything. 2000, now we can start to see. Okay, so that's a better picture of the derivative. So this place where it's 0, 125, that is where f is going to have its maximum. Now is that, for this curve, is it a relative maximum or is it a global maximum? So looking at what the function was, just trying to undo my way back to the good picture, there we go. Okay, it's a parabola. It's a really big honking parabola, but this maximum is going to turn out to be a global maximum. We really only care about kind of where the area is positive. Beyond that, it doesn't have any meaning in the sense of this problem. Okay, so we thought this from the graph. The derivative verified it. 125 feet by 250 feet is the largest area. Now there's some stuff to wonder. I mean, what about This is something mathematicians like to do at the end of a problem like this. What if we didn't do a rectangle? What if we did a triangle? Right? So we could use all 500 square feet on just two sides. And then how big would we want this to be to make the maximum area? Would that maximum area be more or less than the rectangle? What if we turned it into a circle? Right? So maybe we could figure out kind of what the radius would be and compare that area. Would that be more or less? Well, those are good extensions. All right. Okay. Thanks very much.